So, we discuss now problem number 11. It says two compounds A and B decomposes by first order kinetics. The half life of A and B are 45 minutes and 15 minutes. If we start with the same concentration of A and B, then how much will it take for the concentration of A to be 4 times of concentration of B? Okay. So, we start with consider first, okay, let the initial concentration of both A and B be 1 molar, right. So, or therefore, A naught is 1 molar and B naught is 1 molar, right. So, at time t, concentration of A is 4 times concentration of B. So, t is the required time at which the concentration of A will be 4 times of concentration of B. So, t is the required time. Right. So, since both A and B decomposes by first order kinetics, we can write Ka means rate constant of decomposition of A So, half life periods are given. So, 0.693 by half life period of A, T half of A. So, we write Ka is 0.693 by T half is 45 minutes by 45 minutes. So, this is minute inverse. This is the rate constant of decomposition of A. Similarly, Kb, if we consider Kb is the rate constant of decomposition of B, then Kb is again 0.693 by T half B, right. So, we get value of Kb is 0.693 by T half of B is given, this is 15 minutes, so this is minute inverse, right. So, Kb by Ka, okay, so Kb by Ka is 0.693 by 15 times 45 by 0.693. So, you get 3. So, value of Kb by Ka is 3. Okay. Again we know for first order kinetics, T is again for first order kinetics, T is 1 by K ln A by A minus x, right. So, we write for A after time t is, so for A after time t, we write Ta is 45. So, 1 by k is 0.693 by 45. So, we write 45 by 0.693 ln initial concentration of A is A naught. So, we write this one is 1 by concentration of A minus x, if we say this is your concentration of A, right, as A is initial concentration of A naught and A minus x is concentration of A. Similarly, for B after time t, we write Tb is 15 by 0.693 ln 1 by concentration of B. Right. So, we can write, now it says that Ta is Tb, since Ta equals to Tb. So, we write 45 by 0.693 ln 1 by. Now, what is the concentration of A? Concentration of A is 4 times concentration of B. So, 4 times concentration of B is 15 by 0.693. Okay, so ln 1 by concentration of B, right. So, if you calculate this one, so we get basically concentration of B is 0.125. So, this is the concentration of B. So, if we substitute the concentration of B in this expression, so we get Tb. So, Tb is 15 by 0.693 ln 1 by 0.125. So, we get 15 by 0.693 times ln 8, this is in minute. So, if you calculate this one, we get 45 minutes. Okay, so, the time required is 45 minutes. Is 45 minutes. This is very good problem. Next, we move to problem number 12. It says for 40% for 50% completion, if a first order reaction takes 50 minutes at 300 Kelvin temperature and 30 minutes in 340 Kelvin temperature, calculation the activation energy of the reaction. So, we have to use here Arrhenius equation. Okay. So, at 300 K, now first we assume, assume K1 and K2 are the rate constants at 300 Kelvin temperature and 340 Kelvin temperature, that's respectively. Okay. So, we write Q1 is 0.693 by half life is given, okay, and this is first order kinetics. So, T half of T half at 300 Kelvin, right. So, we get 0.693 by T half at 300 Kelvin is 50 minutes. So, this is minute inverse. Similarly, K2 is 0.693 by T half at 340 Kelvin temperature. So, we write 0.693 by 30 minute inverse. So, value of K1 and K2 we have got, right. So, now we will use at Arrhenius equation. Okay. So, according to Arrhenius equation, we write log K2 by K1 is EA by 2.303 times R is the gas constant, times 1 by T1 minus 1 by T2. Here EA is the activation energy, T1 is 300 Kelvin and T2 is 340 Kelvin. Okay. So, if you carry now, if you substitute the values now, so log value of K2 is 0.693 by 30 and value of K1 is also given. So, you get 50 by 0.693 gives you EA by 2.303, value of R is 8.314 and then T1 is 300 minus 1 by 340. Okay. So we get log 5 by 3 is EA by 2.303 times 8.314 times 40 by 300 times 340. So, this is log 10 base. So, you get EA is log 5 by 3 times 2.303 times 8.314 times 300 times 340 by 40. So, if you do it, we get the value of EA. So, the value of EA is 10831.81 joules per mole, or you can write EA is in kilojoule unit, we write 10.83 kilojoules per mole. So, this is the value of activation energy. Next we discuss problem number 13. It says the rate constants of a reaction at 500 Kelvin and 550 Kelvin are 0.12 second inverse and 0.35 second inverse. Calculate the Arrhenius parameters. We have to calculate the value of Arrhenius parameter. So, we know, like this is a very similar problem to whatever we discussed just now. So, we know log K2 by K1 is EA by 2.303 times R 1 by T1 minus 1 by T2. So, here we need to calculate the Arrhenius parameter A that we need to calculate. So, in order to calculate Arrhenius parameter, we need to calculate activation energy. So, from this data, we can actually calculate activation energy. So, here K1 is given, K1 is 0.12 second inverse, and temperature T1 is also given 500 Kelvin. K2 is also given 0.35 second inverse, and T2 is 550 Kelvin. So, if we substitute these here, we get log 0.35 by 0.12 is EA by 2.303 R 1 by 500 minus 1 by 550. So, we get EA is approximately, this is 3 we can consider. So, we get log 10 base roughly 3 times log 10 base 3 or log 3 we can write log 3 times 2.303 into 8.314 divided by 50 times 500 times 550. So, if you calculate this one, we get the value of activation energy. So, activation energy value is 48955 joules per mole. Now, we know again we know log K is log log K is log A minus e to the or EA by 2.303 RT. So, we write log K1 or log A is log K1 plus EA by 2.303 R T1. So, we get log value of K1 is 0.12 plus EA value we just calculated activation energy value. So, 48955 by 2.303 times R is 8.314 and the value of T1 is 500. Okay, so, we get log A is log A value is we get 4.19. So, we get value of A is 15545.52. Okay. So, what will be the unit? Unit will be second inverse. Okay. So, the pre-exponential factor or Arrhenius factor. So, therefore, pre-exponential this A value this quantity A is also known as pre-exponential factor. Pre-exponential factor or Arrhenius factor A is 155.45.52 second inverse. Problem number 14, it says the equation of rate constant for a reaction is given by this expression. Okay, log K is 16.5 times minus 1 times 10 to the 3 by K. Calculate the EA of the reaction. So, we know log K is, we just discussed. Okay, so, log K we know log K is log A minus EA by 2.303 RT. Okay. Go back and check. Okay. So, log K is log A minus EA by 2.303 RT. So, and the expression given is log K is 16.5 minus 1 times 10 to the 3 by T, right. So, if this, suppose this is equation 1 and this is equation 2. So, comparing equation 1 and equation 2, equations 1 and 2, we write A is 16.5. So, the pre-exponential factor is 16.5 and EA, the value of EA is 1 times 10 to the 3 by 2.303 R. So, we get 10 to the 3 by 2.303 times 8.314 joules per mole. So, we get the value of activation energy. So, activation energy is okay. So, EA is 1 times 10 to the 3 by this. Okay. So, we write if we compare this one. So, EA by so if we compare this, we get EA by 2.303 times R. This gives 1 times 10 to the 3. So, value of EA is 1 times 10 to the 3 times 2.303 times R. Okay. So, you get the value of EA. So, EA is 19.147 times 10 to the 3 joules per mole. So, value of EA you get is 19.147 kilojoule per mole. So, the activation energy is 19.147 kilojoule per mole. Next, we move to problem number 15. It says activation energy for a first order reaction is 50 kilojoule per mole. A 10% solution of reactant is kept at 35 degrees Celsius for 30 minutes and 20% of the reactant decomposes. So, 10% solution of reactant is kept at 35 degrees Celsius for 30 minutes and 20% of the reactant decomposes. What will be the percent decomposition in the same time if the 25% solution is kept at 48 degrees Celsius? Active energy. So, assume that activation energy remains same during the temperature change. So, we know at 35 degrees Celsius, or assume, let us consider K1 is the rate constant at 35 degrees Celsius. Okay, so K1 is 1 by T ln A naught by A, concentration of A naught by A. Now, okay, now you say concentration of A naught is A. Okay. Say we consider that concentration of A naught is A. So, concentration of A is A minus, this is A naught, not A naught, A 20 A by 100. So, 20% decomposes, right? Okay. So, if we do it, we get 0.80 A. So, that is the value of A. So, Q1 is 1 by 30 because T1 is first temperature. So, yeah, first time. Okay, time here is 30 minutes. Okay, when 10% solution is kept at 35 degrees Celsius for 30 minutes. So, T1 is 30. So, 1 by 30, then ln, okay, A naught is A by 0.80. 80A. Okay. So we get the value of K1. K1 we get 0.0074 minute inverse, or you can write 7.4 times 10 to the minus 3 minute inverse. This is the rate constant of rate constant K1. Similarly, K2 is okay. So similarly K2. Okay, so in order to calculate K2, we need to use Arrhenius equation. So we get so now we calculation of K2. Okay, it says log K2 by K1 is EA by 2.303 times R 1 by T1 minus 1 by T2. Okay, so we get log K2 by 7.4 times 10 to the minus 3 is EA by 2.303 times R. Now, what is the value of T1? T1 is here, T1 is 35 degrees Celsius, means 308 Kelvin, and T2 is 48 degrees Celsius. Okay, 48 degrees Celsius. So this gives you 321 Kelvin, right? So 1 by 308 minus 1 by 321. Okay, so get log K2 is okay. So if we calculate this one, you get log K2 is minus 1.7874, or K2 is 0.0163 minute inverse. So we got the value of K1 and K2. Now let the percentage decomposition at 48 degrees Celsius is X. Okay. So A is 100, suppose. So A minus X is 100 minus X, right? So K2 is 1 by 30 ln 100 by 100 minus X. So value of K2 we have already got. So 0.0163 is 1 by 30, and then ln 100 by 100 minus X. So you get ln 100 by 100 minus X is 0.489. Okay, so you get 100 by 100 minus X is 1.63. So you get X is 38.6. Therefore, percentage decomposition at 48 degrees Celsius will be 38.6%. This is a very good problem. Next we move to problem number 16. It says the Arrhenius rate expression K times K is A e to the minus E A by RT, where A is not temperature dependent. Assume it weakly depends on temperature A, as A is B times T to the M, then the rate expression becomes K equals to B T to the M e to the minus E B by RT. What will be the relation between EA and EB? Okay. So we know Arrhenius rate expression. We know Arrhenius rate expression K is A e to the minus Ea by RT, right. Okay, so if we take log, so we get ln K is ln A minus Ea by RT. We are taking log of both sides. Okay. So we get, if we differentiate this one with respect to temperature, we get d ln K by dt is, so this is temperature independent. Okay, this is 0 ln d ln A by dt plus Ea by RT square. Suppose this is our equation 1. So again I am telling this is 0 because A says that it is not temperature dependent, okay, as A is independent of temperature. Okay. Now if A is weakly temperature dependent, okay, as it says, okay, so if A is weakly dependent on temperature, okay, then we write temperature and A is B T to the M, then we can write K is B T to the M, right, e to the minus E B by R T. That is what it says. It becomes K is this. Now you can take the log of both sides, so you get ln K is ln B is constant, so ln B minus M, plus M ln T minus Ea by RT, right. So d ln K by dt, so this term is 0 considering B is a constant term independent of temperature, and for this one you get M by T minus, not minus, this is EB not Ea, this is EB as said, okay, this is EB. So you get EB plus EB by RT square. Suppose this is equation 2. Okay. Now if we compare equation 1 and 2, we get basically, because d ln K dt in both in the both expression we calculated d ln K by dt. Okay, so we write, so our equating equation 1 and 2, equating equation 1 and 2. So we write Ea by RT square is M by T plus EB by RT square. So if we multiply both sides by RT square, we get Ea is MRT plus EB plus EB. Okay, so we get Ea minus EB is AMRT. So option A is correct. Option A is correct. This is also a nice problem. Next we move to problem number 17. It says, for an endothermic chemical reaction, which of the following statement is correct? So endotherm is delta H is greater than 0. With increasing temperature, forward rate increases and backward rate decreases. Option A says. Option B is, with increasing temperature, backward rate increases and forward rate decreases. Option C says, with increasing temperature, both backward rate and forward rate increases. And option D says, with increasing temperature, forward rate increases and backward rate stays unaffected. Okay. This is very simple problem. Okay, so this is endothermic chemical reaction. So answer C is correct here. Okay, so this is very simple problem. Next we move to question number 18. In a reversible reaction, 2NO2 goes to N2O4. If the rate constants for forward and backward reaction are K1 and K2, then what will be the rate of disappearance of NO2? Okay, so the reaction is reaction is 2NO2 goes to 2NO2 N2O4, and the rate constant of the forward reaction is K1 and rate constant of backward reaction is K2. Okay, so rate of disappearance of NO2 is, if we say, so we write rate is minus D concentration of NO2 by dt, and now we have half term here because we have the two term here, so this is half we get. Okay. Now, if this is the case, so this NO2 goes to N2O4, so it will be your for forward reaction you get K1 NO2 square, okay, and then this is the formation here, so you get K2 N2 4, right. So back in the backward direction NO2 is formed from N2O4. So we write minus D concentration of NO2 by dt is twice K1 concentration of NO2 square minus 2 K2 concentration of N2O4. Again, this is a very simple problem. So we move to problem number 19. It says a reactant A undergoes parallel reaction. A goes to B with rate constant K1 and activation energy E1. A goes to C with rate constant K2 and activation energy E2. If E2 equals to 4 E1, then what will be the relation between K1 and K2? So it says, so A goes to B with rate constant K1 and A goes to C. It's parallel reaction, right? So A goes to C with rate constant K2, right? Now from Arrhenius equation, you can write K1 is A1 times e to the minus EA for reaction 1 by RT, and K2 is A2 e to the minus EA 2 by RT. So this is equation 1 and this is equation 2. So if we divide what it says, it again says E2 equals to 4 E1. Okay, so activation energy of reaction 2 means when A goes to C is 4 times of the activation energy of reaction when A goes to B. So if we divide K1 by K2, so K1 by K2 gives A1 by A2 and e to the minus EA1 minus EA2 by RT. Okay. Now what is the value of EA2? Now if we substitute the value of EA2 by 4 E1, we get K1 by K2 is A1 by A2 e to the minus, now EA1 minus 4 EA1 or we write E1 here. So, minus E1 minus 4E2, 4E1. E2 is 4E1, so by RT. So, we get K1 by K2 is E1 by A2, we say A is a constant term. So, we get e to the minus plus 3A1 or 3E1, sorry, this is E1, 3E1 by RT. Okay, so, where A is constant, where A is A1 by A2 equals to constant. So, we get K1 by K2 is, or K1 is K2 times A e to the 3E1 by RT. So, this is the answer. Next, we move to problem number 20. It says A undergoes a parallel reaction of first order such that A goes to B, rate constant is given, K1 is 9.4 times 10 to the minus 5 second inverse, and A goes to C with K2 is 2.4 times 10 to the minus 4 second inverse. The percentage distribution of B and C will be. Okay. Now, for a parallel reaction, percentage distribution of A is K1 by, we already discussed this one, times 100. So, value of K1 is given 9.4 times 10 to the minus 5, and value of K2 is also given 9.4 times 10 to the minus 5 is the value of K1 plus 2.4 times 10 to the minus 4 is the value of K2, so times 100. So, we get 28.1%, and percentage distribution of B is K2 by K1 plus K2 times 100. So, again we substitute the values of K1 and K2. The value of K2 is 2.4 times 10 to the minus 4, and value of K1 is 9.4 times 10 to the minus 5 plus 2.4 times 10 to the minus 4. If we calculate this one, we get the value of the percentage distribution of B is 71.99%. So, 71.9%. So, option, therefore, option A is correct.